Next, this theorem we have not stated earlier, or possibly have stated, but we have not proved it. This theorem is saying that the following statements are equivalent. So, here a point A which has this property, this continuity property at the boundary. A is the point on the boundary, and if you have this continuity property, so this left hand side is part of the solution of the Dirichlet problem, correct? The solution form. We cannot accept that as a solution because it is valid only inside the boundary, inside the domain. So this is a continuity property at the boundary, and the second is A is a regular point on D for D, and third point is that that if you have a fixed epsilon, then stopping time, the exiting time is more than epsilon, the probability decreases as your initial point approaches to the boundary. Okay, so we are going to prove today only part 1 to 2. Okay, well, that 1 implies 2. Okay, so what is there? A has property, this continuity property, and you have to prove that A is regular for D. We are going to take the contrapositive method, prove by contradiction. We would consider that A is irregular for D, and then we have to get contradiction here. So, we have to get that, okay, this is not equal. Okay, so that is our goal, and that we need to get for any function f which is boundary measurable and continuous at point A. Okay. So, I have not written here the nature of f, but I think I have written in earlier slides, in this slide or maybe in earlier slide. Okay. So, the first part is that we use this inequality that probability A intersection B is greater or equals to probability of A minus probability of B complement. So, the derivation is noted here. It is the simple result that A intersection B and A intersection B complement, these two are disjoint events. So, sum of the probabilities is same as the probability of the union. So, the probability of the union is A, probability of A, and then probability of A intersection B is equal to P of A. So, this part is on the right hand side now, subtraction sign, minus sign, A intersection B complement. So, this part we are replacing by a larger set, but negative sign. So, we are going to get less than greater or equals to sign, probability of A minus probability of B complement. Okay, we are going to use that somewhere here. So, we, as I have mentioned, that we are going to take the proof by contradiction approach. So, we consider 0 is irregular. So, without loss of generality, we assume the point A is 0 here, origin. Okay, and we assume that 0 is irregular. What does it mean? The meaning is that if we start Brownian motion from 0, so W0 is equal to 0, then given that the probability that positive exiting time is 0, that has probability 0. Okay, so for a regular point, this is 1. So, now what do? We consider this probability, conditional probability, that probability of W tau sigma D belongs to BR. What is BR? BR is the ball of radius R around 0, given W0 is equal to 0. Why are we talking about this? Because using this help, we can actually come to this point. Okay, so here we basically want to prove this, correct? Prove that this is not true, correct? We need to prove this expectation of this not true about W tau D, correct? We need to do this. So, we start from here. Probability that W sigma D belongs to the ball of radius R when W0 is equal to 0. Okay. So, here if imagine that ball of radius R, and then R you have several different values, decreasing values. Then, so if you say that, okay, sigma D is a number that when it leaves the domain, if your R is smaller than the ball is smaller, then this event might not remain true. Okay, but however, if it is true for some particular R, for larger R also this is true. So, as R is decreasing, this is actually nested decreasing events, correct? So, when we have such type of limit, so nested decreasing events, the limit R tends to 0, limit of this type of family of events is exactly equals to probability of intersection of these events. Okay, because when we have nested events. That is true actually not only for probability measure, but any finite measure. Okay, but for infinite measure it need not be true, but for any other finite measure also this is true. So this is probability of intersection R positive. So here R is going to 0. Okay, positive of the same event. The W sigma D is in BR given. So there is a typo. This is W0. W0 is equal to 0. Okay, so this is corrected here. So now, what is this intersection? That W sigma D Brownian motion at the time of this sigma D stopping time is in the ball of radius r, and where this is in R for all positive r. That means that this is exactly 0, because 0 is the only one single point, so that these things would be satisfied. So W sigma D is in the singleton 0, basically this is 0. Okay, but what is the probability of this event? We note that in Brownian motion for dimension D, dimension more than or equals to 2, Brownian motion starts from a particular point, then there is a 0 probability that you return to that same point. Okay. However, this is not true for one dimension, correct? Because one dimension is like going right or left. So when it goes right, okay, there is a probability also it would come to left, and it would go to the negative side only by crossing 0. So if you start from 0, it would always cross 0. Okay, but in two dimension it is not the case. The probability that another time, future time, it would again hit 0. Okay, and this sigma D is defined using the boundary of the domain. So that probability is 0. So this is 0. Okay. So what is the point? The point is that this limit is 0. Okay. So that means this conditional probability could be as small as possible. So if I choose sufficiently small r, I can make this probability smaller than any predetermined number. Okay. Good. So we start with say 1/4 is a small number. Okay. Not too small, 1/4, and we fix R positive such that this thing is less than 1/4. Anyway, this thing goes to 0 as R tends to 0, but we choose a particular R such that this is less than 1/4. Why 1/4? That would be clear, that it would appear in the steps of the proof. We choose a sequence of delta n. Delta n is decreasing to 0, and we keep delta n smaller than R. Okay. Then we define the time when the Brownian motion leaves the ball of delta n. This time would decrease as n increase, because delta n goes to 0, correct. So delta n will be smaller and smaller boundary, and the time for Brownian motion to take the time the Brownian motion would take to leave the ball would be shorter and shorter. So the sooner the Brownian motion would leave, as delta n would be the smaller. Okay, so that is my tau n. So tau n goes to 0 almost surely. Okay, so tau n is a stopping time that would go to 0 almost surely. So we are constructing several different random variables and sequences for our proof, just because this is required. Okay, so it is unavoidable. Okay, so tau n converges to 0 almost surely with respect to this conditional probability. That again there is a typo. This is W0. Okay, so given W0, so conditional probability with respect to this conditional probability, this tau n goes to 0. This is clear. Now we ask this question, that what is the probability that tau n is less than sigma d given W0 is 0. Okay, for a particular n, this probability could be some number which need not be 1, because it need not be sure event. However, as tau n goes to 0, so for a large n, because sigma d does not depend on n, correct. So whatever the realization value of this, for every realization there will be a large n such that tau n will be even smaller than sigma d, whatever the value of sigma d. So as n tends to infinity, for each and every sample point, etc., we are going to say that would be go to 1. Okay, this probability would converge to 1. It would become sure even that it would of course be smaller than sigma d. So we get probability that tau n less than sigma d, okay, given W0 is 0 is equal to 1. Okay, Now, since it is converging to 1, so we can make this thing as large as possible, like less than 1, but any number which is less than 1, it can be above that. We can make it, we can find out that such n. So, here what we do, we choose one large capital N. Okay. So, see here we have fixed one r, and that we have not changed here, and here we are fixing again another thing, that is capital N. And now for all n naught, small n naught, which is equal or more than capital N, the probability of tau n naught less than sigma d is more than a half. So, we are taking the threshold half. Okay. So, since this thing is converging to 1, increasing to 1, I mean it would of course overcome half threshold. So, capital N is such number, and this is deterministic number, because this is deterministic sequence. When you find a probability, it is the sequence of deterministic numbers. Okay. So, we find that, okay, so we fix that n as capital N such that for all n naught greater than capital or equals to capital N, this probability is greater or equals to half. Now, what we do, we consider this sequence of events, that tau n is less than sigma d for that probability, okay, what we have obtained here, and also the random variable w tau n. Tau n is a random stopping time, okay, stopping time. W is a Brownian motion. So, the value of w at the time of tau n. So, let us recall what is the tau n. Tau n depends on r, correct? I mean delta n, correct? And delta n converges. So, like it is like hitting time of the ball of radius delta n. Okay. So, given this and this, the probability that tau n belongs to d, okay, where tau n is less than sigma d. Okay. So, let us try to understand why is it 1. Okay. So, when tau n is less than sigma d, okay, so that means the time tau n still sigma d is still larger, that means the Brownian motion did not leave the domain. Okay. Tau n is smaller than sigma d. Since it did not leave the domain, that means it is inside the domain. So, when tau n is less than sigma d, then if we ask what is the probability that w tau n is in d, of course, it is a sure event, it is 1. Okay. So, probability that w tau n belongs to d given sigma d is 1. Okay. Fine. So, here there is no limit on it. Okay. Now, we use this 1/4 number. We remember that 1/4 is greater than this probability. W sigma d is in the ball of open ball of radius r. The conditional probability of this event given w0 is equal to 0. Okay. So, now we compute further. What we do is that here we are writing one subset of this, so sub event. So, we are going to get greater or equals to sign here. What is this sub event? That this is as it is, but we are asking even the intersection with this comma stands for intersection. So, this event and also this event is also true. Okay. When you are asked that, okay, two events simultaneously true, then it is intersection, and then of course, this is subset of that. So, we are going to get greater or equals to sign here. So, here the event is tau n naught is less than sigma d. Okay. So, where n naught is greater or equals to capital N. Okay. Okay. So, as such, for defining this tau n, we did not care about whether it is outside the domain or inside the domain, nothing, correct? Okay. But so this is not a sure event or something, this is just an event. So, tau n naught is also we are requiring that is less than sigma d. Okay. So, this probability we can write down as an expectation also, correct, because probability of A is nothing but expectation of indicator function of A. Okay. So, we write down that way. So, this event W sigma d belongs to BR, we write down W sigma d belongs to BR, indicator function. Yeah. So, actually better notation is 1 BR and then of W sigma d. right? Because if sigma d is in BR, then it is 1, otherwise 0. Okay. And here it is that this event tau n naught is less than sigma d. Okay, so I have these two, intersection is like product of these two indicator functions expectation, but instead of one expectation we have taken two expectations. Why? Because this is the probability I need to find given w0 is equal to 0. Okay, however, we are using tau property of expectation. We are conditioning even further inside with a finer sigma algebra in between. Okay, that here the sigma algebra is a time 0, but here a tau n naught. Okay, so in tau n naught would be 0 or positive, right? So it is finer than this sigma algebra. So we are getting expectation of this thing given f tau n naught given this. Okay, now what we do, we observe that this quantity, okay, this quantity is f tau n naught measurable. Why? Because to decide this, you do not need to wait till sigma d, you just need to wait till tau n naught. If you run the Brownian motion simulation or Brownian clock, okay, you run the clock and observe the Brownian motion and stop at the time of tau n naught, and then whatever you have observed, that will be sufficient for answering this question whether this is true or not. Because by that time you know that whether Brownian motion has layered the boundary or not, whether it touched the ball or not, everything. So that would be clear. So you would be able to say that. Okay, so this is measurable with respect to f tau n naught, and therefore conditional expectation of this event given f tau n naught is same as this random variable, which is f tau n naught measurable, comes out of the expectation. Then you have only expectation of this random variable given f tau n naught, but this random variable is again an indicator function. So expectation of indicator function is probability. So you write in probability directly. So this part would be probability of this event w sigma d belongs to BR given f tau n naught. So here this part we are taking outside of expectation, and then inside expectation of indicator function becomes probability. The expectation of indicator function of a set of an event is probability of that event. So here you get w sigma d belongs to BR given f tau n naught. Then this whole thing, this conditional probability is a random variable, is f tau n naught measurable random variable, and this is also f tau n naught measurable random variable, and we have a conditional expectation of product of these two random variables given w0 is equal to 0. Yes, this bracket should appear here. Okay, so now our goal is to compute this expectation. We know how to compute expectation. Expectation of a function of a random variable, if we want to compute, say expectation of small f of capital X, X is the random variable. What do? We have integration f of small x times the probability density function of the random variable we consider, if it has a PDF. Okay. Otherwise, we just take CDF. If it is multidimensional, etc., then we just take the law, the distribution measure of the random variable. Okay, we integrate with respect to that. Okay, we do exactly the same thing here. For this, since we need this, okay, so what we do is that probability of W. So instead of sigma d, I am writing tau d. I am explaining why can you do that, okay, in a minute. So probability of tau d in BR given now here f tau n naught. So here we are using the strong Markov property of Brownian motion. The tau n naught is the stopping time. So the future distribution given this filtration at tau n naught is same as the future distribution given the present at tau n naught. What is the random variable? So w tau n naught. So this thing appears here. Okay. So actually here this expectation we are doing in this way, and for this part we are doing in this manner, that w tau n naught is equal to x, and then we are going to use the distribution of w tau n naught given w0 is equal to 0, okay, because we need to find out this expectation, correct. And this random variable is now simple because we are using strong Markov property of Brownian motion. So now it is just like w tau n naught is equal to x. X is just a vector in d-dimensional space, and then the law is w tau n naught is in dx. So this is just a notation to show that basically I am picking up the distribution measure of w tau n naught, okay. So and given w0 is equal to 0, but we do not write w0 is equal to 0, we again use Bayes rule, we condition and then take and multiply with the probability. So this w tau n naught belongs to dx. So given tau n naught is less than sigma d into probability tau n naught less than sigma d. So what is this? This whole product is basically intersection of these two, the w tau n naught dx, and this is true, okay. And why are you doing that? Because here we have that tau n naught less than sigma d, we need to do expectation on this, correct. So we need this, so we are having that intersection of these two things that we are doing using Bayes rule, that conditional probability and then product. Since we have incorporated this here, so what are we left with? We are left with that this x we have to run among its scope. So what is the scope of x here? So w tau n naught anyway by definition is on the boundary of the ball of radius delta n, okay, that is its scope. So the boundary of ball of radius delta n naught, okay, around 0, okay. So this, however, why are we taking intersection with d? Thing is that so that we can sigma d2, we can write down tau d here. Why? Because here when w tau n naught is falling outside d, that means that ball of radius delta n naught is the part which is outside d. If that is the present space x, that means the sigma d occurred before, sigma d already have occurred, okay. So but that is excluded, correct, because that is excluded. So only when those cases it would be of course in d, okay. So that should be excluded, and in this scenario then sigma d is in Br, okay. So that means that is same as tau d. Why? Because sigma d differs from tau d only when that tau d is 0, right? Only when, not tau d, say when, I mean it just goes immediately, it leaves the boundary, okay. Otherwise if it immediately does not leave the boundary, then it is different. So here of course it does not leave immediately in the boundary, because here it is tau n naught is in x and everything is inside till some positive time. So I can replace sigma d by tau d here. Okay, so from this step to this step had lots of argument to justify, okay. I mean, but yeah, so I possibly if I write maybe in between steps in lecture notes, possibly I would write down more steps, okay. Now we are going to estimate this thing. We are going to use the values what we have obtained earlier. Probability tau n naught less than sigma d given w0 is 0 is greater or equal to half. So here tau n naught less than sigma d, tau n naught less than sigma d, this appears, okay. So here I have not written, but it is there. I mean basically I should have written, but I have just presumed that it is there all the time. The w0 is 0, okay, so because we cannot escape from it, w0 is 0. So this thing is greater or equal to half, so I am writing half here, and then the remaining terms are here the d intersection boundary of ball here, and probability w tau d belongs to b here, exactly tau n naught. So here So if I start with 0, yes, it is not a typo. This is okay. Why is it okay? Because now we given this, the tau at tau n naught, w tau n naught is equal to x, the probability that w tau d is in BR, and instead of that what we are doing is that we are declaring this as our starting time. So if we consider as if the Brownian motion at tau n naught, and there it is regenerative starting from there itself, and then since it is Markov, it has memoryless property. So from there onward, then anyway this is inside the boundary because d is intersection this, so it is anyway inside the boundary. So then we look at that the probability that w tau d is in BR, okay, given w0 is equal to x, and then probability, this is exactly the same as before, w tau n naught, this is a typo, belongs to dx given tau n naught is less than sigma d. Okay. So next what we do is that we are trying to again get a lower bound of this value. So how are we doing that? We are taking infimum over all possible x, because x is anyway running in this domain d intersection boundary of ball of radius delta n naught x, okay, n naught 0. So here if we take infimum over all possible these things, okay, and then the remaining thing would be this, and integration of this measure. So basically here instead of dx I should write down this whole thing here, d intersection del b delta n naught, correct. So this is integration where this is the measure, this is the function, this function I am replacing by the infimum, and then we are going to get it. Okay. So we have 1/4 is strictly greater than half into this value. So we are actually looking at some contradiction, correct. So now what we do, we construct some xn naught, because this part is small, so we can always find out an xn naught such that this whole thing is less than or equals to half. So here we have what we have obtained is that 1/4 is strictly greater than this expression, and half is already there. So this product of these two quantities is strictly less than half, but right hand side expression, the probability is exactly equal to 1. So this infimum amount is strictly less than half. The reason that right hand side probability is equal to 1 can be seen in the following manner, that given the fact that tau n naught is strictly less than sigma d, that means the Brownian motion at time tau n naught did not leave the domain. So w tau n naught is in domain D. Here there is a typo, it is w t n naught, okay, 0 is missing here. And by definition of tau n naught, w tau n naught is on the boundary of ball of radius delta n naught. So probability that w tau n, so it is a sure event, the w tau n naught should be on D intersection the del B delta n naught. So we have some value here at, I mean the minimum is strictly less than half. Since it is strictly less than half, so I can find out some point x which is also less than half. If I say infimum is less than or equals to half, then I cannot assume, but here I have strict inequality. So I have infimum is strictly less than half. Since infimum is strictly less than half, so I would be able to find out some x, particular x. So that is the thing I am writing, some x here such that w tau d belongs to BR. So w tau d belongs to BR, this probability is less than or equals to half. So this we can do, and we call this x is x n naught. Okay, the reason we are denoting by n naught is because that we are talking about ball of radius delta n naught. So keeping that in mind, we are writing it x n naught, this value. Okay, So, that we can do for each and every n naught greater or equals to capital N, because there is nothing special about this n naught, because for this is true for any n naught greater or equals to n. We can always get this exactly the same thing. So, for any n naught greater or equals to n, we would always be able to get, I mean, of course, then as n naught is large and larger, your ball of radius delta n naught is also becomes smaller and smaller. X n naught is always on the boundary. So, x n naught is also coming closer and closer to 0. However, we are always assured to find out such x n naught such that this condition probability is strictly less than or equals to half. So, you got a sequence x n naught along which if you run, this probability would be less than or equals to half all the time. Okay. So, choose a function f now, okay, from that boundary of the domain, the real valued function, which is bounded and continuous, such that f is equal to 0 on the boundary minus br. Okay. So, if you have the ball of radius r, okay, so beyond that. Okay, so there is a typo here. This is and, correct? Yes. So, f is less than or equal to 1 inside the ball br, here comma, okay, here there should be comma, f of 0 is equal to 1. Okay. So, we have now just I mean, what is the assurity that such function would be there? Thing is that I can this is easy to function you are taking that at 0 it is 1 and then it is decreasing to 0, where I mean, so it is always less than or equals to 1, okay, and so 1 is the maximum point, at 0 it is the maximum point, and 0 is on the boundary, because we are looking at 0 as irregular parameter, 0 is on the boundary, correct, and there when that boundary part outside the ball of BR, so there it is becoming 0. So, yeah, I think it is good if I draw. Imagine that this is 0, this is ball of radius r, okay, and this part is the boundary of the domain, this is domain D, and this is origin. Okay. So, now the function f, what we are constructing is 1 at 0 and 0 here. Okay. The function f is defined on the boundary of the domain, okay, boundary of the domain. Of course, boundary of the domain is a closed set here we are going to get, because D is open connected domain, and here what we get is that a function, I mean, the existence of this function is assured, correct? We know that, okay, this is a closed set, this is a closed set, they are separated. We can do that, we can we can create a function f which is 1 at this point and 0 here, clear? So, that is the choice of the function. So, we choose function that which is 0 on the complementary part of the ball, but on the boundary, and which is 1 at 0, and this is comma, and then f is strictly less than or equals to 1. Okay. So, you can construct such function. Okay. So, now by taking this function f, imagine remember that what was our goal? Our goal is to prove by contradiction. So, for that this part says that this is true for all bounded measurable function f which is continuous at the point A. So, to contradict, I just need to figure out one single example sufficient for which it does not hold. sufficient. So here my function f is continuous at the point a here is 0 origin, correct, the point on the boundary. Okay, fine. So now we consider this lim sup n-tends to infinity, because I don't know the limit exists, f of w tau d given w sigma is equal to xn. Okay, so let us see what is this factor. This is exactly this quantity, expectation of f of w tau d given w 0 is equal to x here. Okay. Okay, so where x tends to a, but for us a would be 0 here. So expectation of f of w tau d given w sorry, here it is a typo, it will be 0, w 0 is equal to xn. Now we are replacing this part by this. Okay, so since f is less than or equal to 1, okay, so if we replace f by indicator function of br, okay, so then inside br it is 1 always, but f is always less than or equals to 1 there, we are replacing that. So this would be, of course, we are going to get this less than or equals to sign here. So lim sup n tends to infinity expectation of indicator function of w indicator function of say br of w tau d given w 0 is equal to xn. Now we know that expectation of indicator function is probability of the event itself. So this conditional expectation is conditional probability that w tau d belongs to br given w 0 is equal to xn and n tends to infinity. And here what we have constructed is that after capital N onward, capital N is fixed. For every n naught, we can choose some xn naught along which this would be always less than or equal to half. So here now we are choosing exactly considering that xn. Okay, we are keeping that xn and letting n tends to infinity. So then after capital N onward, this value would be always less than or equals to half. So this lim sup would always be less than or equals to half. So that is strictly less than 1, but 1 is a value of f at 0. Okay, so we got that this is not equals to this, is strictly less than this value. Okay, whereas xn still converges to 0, correct, because that is the point that x converges to limit. Okay, so here to get, I mean, for proof by contradiction, if we have assumed the negation of this to conclude the negation of this, and here this is true for all possible f etc. But now we have constructed a particular f and constructed a particular sequence xn converging in a particular manner. Okay, and there it did not hold. So when a particular, I mean, if in the multivariable calculus even you find one particular way this limit and this do not hold, then of course total limit you do not have any hope. Okay, and lim sup is not matching, so therefore forget about limit. I mean, okay, so limit would also, I mean, even if limit exists, that would not match. Okay, so we get that this equality do not hold. This does not hold. Okay, so here hence there exists xn decreasing to 0 such that this is not equal to f0, thus 1 fails, hence 1 implies 2. Okay. Thank you very much.